Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. Imagine an e-commerce company during a 40-minute flash sale. The site looks healthy until thousands of shoppers hit product pages and checkout at the same time. Database connections pile up, queries wait in line, and the order system becomes the bottleneck. The answer is not automatically use Aurora. Better queries, indexes, caching, connection management, or a larger database instance might solve the problem. But when a MySQL or PostgreSQL compatible application needs cloud-native storage, high availability, read scale, and capacity options designed for changing demand, Aurora becomes a serious option. If you watched the RDS video, you already know managed relational databases. This video explains Aurora, what makes its architecture different, what problems it can solve, and when paying for it makes sense. By the end of this video, you will be able to do 3 things. First, explain what makes Aurora different from standard RDS for MySQL or PostgreSQL, especially its separation of compute and distributed storage. Second, identify when Aurora may fit a workload better than standard RDS, and when standard RDS remains the simpler, more cost-effective option. Third, explain how Aurora uses reader instances, multi-AZ placement, global database, and Aurora Serverless to address availability and scale. These are useful cloud practitioner foundations, but always check the current official exam guide before treating any product metric as an exam requirement. Picture an e-commerce site running on standard RDS MySQL at 12:01 a.m. on Black Friday. 5,000 shoppers hit product pages and checkout at the same time. Database connections increase. Queries begin waiting. And checkout latency starts climbing. But don't immediately blame the database architecture. First, investigate. Are inefficient queries consuming resources? Are important indexes missing? Is the application opening too many database connections? Could caching reduce repeated reads? Is the database instance simply undersized? Or has the workload actually reached the practical limits of the current architecture? After testing and measurement, suppose the team discovers that the application needs substantially more read capacity, stronger availability characteristics, and an architecture that can adapt better as demand changes. Now, Aurora becomes something worth evaluating. The lesson isn't, RDS became slow, so move to Aurora. The lesson is, find the bottleneck first. Then choose the architecture that solves the actual problem. Amazon Aurora is AWS's cloud-native relational database service compatible with MySQL and PostgreSQL. Aurora is managed through the Amazon RDS service family. But it is not simply a switch you enable on a standard RDS MySQL or RDS PostgreSQL instance. Aurora has its own distributed storage architecture and its own cluster model. Your application can often reuse familiar MySQL or PostgreSQL drivers, tools, SQL patterns, and frameworks. But compatibility is not identical behavior in every case, so test application features before a production migration. Aurora is fully managed. AWS operates much of the underlying database, infrastructure, and platform. Your team still owns database design, query tuning, security configuration, networking, backup requirements, monitoring, cost decisions, and the availability architecture you choose. Aurora separates compute from persistent storage. Your writer and reader DB instances provide database compute and memory. They connect to a shared Aurora cluster volume that stores the durable data. That shared storage design means Aurora can add reader instances without copying the entire database to a new storage system first. The cluster volume is distributed across 3 availability zones in a single AWS region. Aurora synchronously replicates data to 6 storage nodes across those zones, which supports durability and helps the cluster tolerate an availability zone problem. That is the cloud-native idea in practical terms. Compute can be sized or scaled separately from the shared, distributed storage layer. It is a different architecture from simply placing one traditional database instance on a larger server. Quick checkpoint before we get to durability. Which 2 database engines is Aurora compatible with, and what does fully managed actually mean? Say both out loud. Aurora's storage layer is designed for high durability. Your cluster volume is distributed across 3 availability zones, and Aurora keeps multiple copies of the data, so the storage remains resilient even if database instances become unavailable. But high availability for the application depends on more than durable storage. A fast writer failover requires a suitable reader instance that Aurora can promote, ideally placed in a different availability zone from the writer. Aurora is designed for up to 99.99% availability in a single region and up to 99.99999% availability across multiple regions when you use the relevant architecture. Those are AWS design targets, not a promise that every cluster configuration gets the same outcome. The lesson is, Aurora gives you a resilient foundation. Your cluster topology, reader placement, connection handling, and recovery design determine how well the application uses it. Suppose the availability zone hosting your Aurora writer has an outage. The storage volume still has copies of the data in other availability zones. If your cluster has a reader instance in another availability zone, Aurora can promote that reader to become the new writer. Your application experiences a brief interruption, then reconnects through the cluster endpoint, which points to the current writer. If there are no reader instances, Aurora must create a replacement writer during the failure. The data remains durable, but recovery can take longer. So do not confuse durable storage with a complete, high-availability design. For important production clusters, place one or more readers in different availability zones, use the correct cluster endpoint, and test how your application handles a connection interruption. Aurora is designed for demanding MySQL and PostgreSQL compatible workloads through its distributed storage architecture and flexible compute options. AWS publishes performance benchmarks, but a benchmark is not a promise that every application becomes faster after migration. Performance still depends on query design, indexes, instance capacity, connection behavior, read and write patterns, storage configuration, and the application around the database. So use the right mental model. Aurora can provide an architecture that supports high throughput and scale. It does not turn an inefficient query into an efficient one. Measure the workload, identify the bottleneck, then choose the fix. Aurora is not standard RDS MySQL or PostgreSQL with a performance setting turned up. Standard RDS is a managed relational service that can be an excellent fit for many steady workloads. Aurora is a separate cluster-based relational service compatible with MySQL and PostgreSQL. It separates compute from distributed storage and supports features such as reader instances, Aurora Serverless, and global database. Aurora also provides a resilient storage foundation across availability zones. But high application availability depends on the topology you configure: reader placement, availability zone distribution, cluster endpoints, and application reconnection behavior. Treat Aurora as a different architecture to evaluate, not as an automatic upgrade from standard RDS. One quick distinction: Aurora's distributed storage helps protect data across availability zones. But durable storage alone does not guarantee the fastest application recovery after a writer failure. For faster failover, use eligible reader instances in different availability zones so Aurora has a ready promotion target. Then make sure the application connects through the cluster endpoint and can handle a brief connection interruption. Remember, storage durability protects the data. Reader topology improves writer recovery. An Aurora cluster can have up to 15 Aurora replicas, also called reader instances. Reader instances run read-only queries and help offload read traffic from the writer. Applications commonly use the reader endpoint, so Aurora can distribute read-only connections across the available readers. Because the reader instances use the shared Aurora cluster volume, Aurora typically keeps replica lag very low, often much less than 100 milliseconds. But lag can grow during periods of heavy writes, so the application must not use a reader for a query that requires the absolute latest committed data. Reader instances also improve availability. If the writer fails, Aurora can promote an eligible reader to become the new writer. For important clusters, place readers in different availability zones and define promotion priorities deliberately. Aurora reader instances have two important jobs. First, they scale eligible read traffic. An application can send product searches, account history, dashboards, and other read-only workloads through the reader endpoint instead of sending every request to the writer. Second, readers can be failover targets. If the writer has a qualifying failure, Aurora can promote an eligible reader to become the new writer. For an important production cluster, place readers in different availability zones, choose appropriate promotion priorities, and test how the application reconnects during failover. Readers are not just performance tools. They are part of the availability design. Aurora Global Database is for applications that need Aurora across multiple AWS regions. It has one writable primary region and up to 10 read-only secondary regions. Writes go to the primary Aurora cluster. Aurora then replicates changes asynchronously to the secondary regions, typically with latency under 1 second. That design supports two main use cases. First, global read performance. Users can read from a nearby secondary region. Second, regional disaster recovery. If the primary region has a serious outage, you can fail over to a secondary region. Aurora Global Database is not an active cross-region write database. The primary region performs writes. You can configure write forwarding from secondary clusters in supported configurations, but the primary remains the writer. Aurora Serverless is an on-demand auto-scaling configuration for Aurora. Instead of choosing one fixed instance size, you set a minimum and maximum capacity range, and Aurora adjusts compute and memory capacity as application demand changes. Capacity is measured in Aurora Capacity Units, or ACUs. Aurora Serverless can scale in small increments, so it can fit development and test systems, new applications with uncertain demand, variable e-commerce traffic, multi-tenant systems, and other workloads that change over time. You pay for the database resources you consume. That can reduce over-provisioning, but it does not make capacity planning disappear. You still choose the minimum and maximum ACUs, decide on readers and availability zone placement, configure backups and security, monitor performance, and estimate cost. Aurora Serverless automates capacity adjustment. It does not eliminate database architecture. Match the scaling problem to the right lever. If the writer is short on CPU or memory because of heavy write processing, evaluate a larger DB instance class. If eligible read traffic is overwhelming the writer, add reader instances and route those reads through the reader endpoint. If database demand changes substantially over time and the workload fits a supported autoscaling configuration, evaluate Aurora Serverless with a sensible minimum and maximum ACU range. The question is not, how does Aurora scale? The question is, which part of the workload needs to scale? Use vertical scaling when the writer needs more compute or memory. That means moving to a larger DB instance class. Use horizontal read scaling when eligible read traffic needs to be distributed. That means adding Aurora reader instances. You can use both in the same cluster. A writer can need more capacity for transactional work while readers handle catalog searches, dashboards, or other read-heavy traffic. Choose the scaling method that matches the bottleneck. Adding readers does not solve a writer CPU problem, and a larger writer does not automatically distribute read traffic. Aurora cluster storage grows automatically as persistent data grows. You do not pre-provision a fixed storage volume before writing data, and supported Aurora Engine versions can grow the cluster volume to as much as 256 TB. You are charged for the storage you use, but storage is not the entire Aurora bill. Aurora also has different storage configurations. Aurora Standard includes charges for database capacity, storage, and I/O requests. Aurora I/O Optimized uses a different cost model with no separate read-or-write I/O charge. The right choice depends on the workload. Standard can be cost-effective for moderate I/O. I/O Optimized can make sense when I/O is a large portion of the total Aurora cost. The lesson is not storage is free and automatic. It is storage scales automatically, and you still choose the cost model that fits the workload. Aurora is not the right choice just because an application is large, important, or called enterprise. Start with the requirements. A steady PostgreSQL application that already meets its availability, performance, and recovery requirements on standard RDS may not need Aurora. A MySQL or PostgreSQL compatible application with substantial eligible read traffic may benefit from Aurora reader instances. A workload with meaningful capacity variation may be a candidate for Aurora Serverless. A global application that needs local reads in several regions and a regional disaster recovery design may be a candidate for Aurora Global Database. Start with the workload. Then decide whether Aurora's architecture solves the requirements better than the alternatives. Standard RDS is often a strong fit when a supported engine, a familiar management model, and a simpler or lower-cost configuration meet the workload's needs. Evaluate Aurora when the application is compatible with MySQL or PostgreSQL and benefits from its distributed storage, reader-based read scale, cross-AZ failover design, Aurora serverless capacity options, or global database capabilities. Do not choose Aurora simply because a workload is on premises, because it is business critical, or because a benchmark sounds impressive. Choose the managed relational architecture that fits the application's compatibility, availability, performance, operational, and cost requirements. Name one reason to evaluate Aurora over standard RDS. A MySQL or PostgreSQL compatible workload that needs multiple readers for read scale, a cross-AZ reader topology for fast writer recovery, variable compute capacity through Aurora Serverless, or global reads and regional disaster recovery through global database are all strong answers. Now name one reason to keep standard RDS. A steady workload that meets its engine, availability, performance, and cost requirements without Aurora-specific capabilities is a strong reason. Requirements first, product names second. An Aurora application becomes slow. Do not immediately choose a larger instance. Start with evidence. Look at slow or expensive queries, indexes, database connections, CPU and memory pressure, read traffic, and I/O behavior. Then look outside the database. Network latency, application code, downstream services, and inefficient request patterns can all make a database-backed application feel slow. Only after identifying the bottleneck should you choose the fix. It might be query tuning, an index, connection management, caching, reader instances, a larger writer, or a different architecture. Aurora gives you powerful scaling options. Good engineering still starts with diagnosis. Aurora is not automatically cheaper just because it is managed or because it can scale. Estimate the entire architecture. Consider writer and reader capacity. Aurora Serverless. ACU use if applicable. Storage, I/O configuration, backups, replicas, global database secondary clusters, data transfer, and related services such as RDS proxy. Aurora Standard includes separate I/O request charges. Aurora I/O Optimized has a different pricing model and can be worthwhile for I/O-intensive workloads. A small, predictable database might cost less on standard RDS. A variable or demanding workload might justify Aurora's capabilities and cost model. Use the AWS pricing calculator with the actual region, engine, topology, expected traffic, and storage configuration. That is more reliable than comparing a single advertised hourly rate. For foundational cloud learning, remember the Aurora decision map. Aurora is a managed MySQL and PostgreSQL compatible relational database service with distributed cluster storage. Reader instances can scale eligible reads and serve as failover targets. Aurora Serverless adjusts capacity within an ACU range. Aurora Global Database supports global reads and regional disaster recovery with one primary writer region. Those capabilities are useful only when they match the workload. If standard RDS satisfies the application's requirements with a simpler or lower-cost design, standard RDS may be the better choice. Read the scenario, identify the requirement, then choose the architecture. Aurora uses a cluster model, so launching a usable database is more than one command. First, create the DB cluster. In the command shown on screen, choose an Aurora engine such as Aurora MySQL or Aurora PostgreSQL, provide the DB subnet group and VPC security group IDs, choose encryption, set backup retention, and configure an administrative credential or a managed secret. Then create at least one DB instance inside that cluster with Create DB Instance. That instance becomes the writer. For a high availability design, create one or more reader instances and place them in different availability zones where the engine and regions support that design. The cluster command creates the shared Aurora storage and cluster configuration. The DB instance command creates the database compute that applications connect to. Before running any command, verify the current AWS CLI reference, the engine version availability in your region, your VPC and security group design, and expected cost. Do not present a one-command demo as a complete high-availability production deployment. In the AWS console, open RDS and choose Create Database. Select Amazon Aurora, then choose an engine compatibility option, Aurora MySQL compatible or Aurora PostgreSQL compatible. Choose provisioned capacity or Aurora Serverless based on the workload. For serverless, set the minimum and maximum ACU range. For provisioned capacity, choose the DB instance class for the writer and any reader instances. Then review the production settings. Select a VPC, DB subnet group, and restrictive security group. Keep public accessibility turned off for the typical production design. Choose encryption with AWS KMS. Set the backup retention period, configure monitoring, and review maintenance settings. After creating the cluster, confirm that the writer instance is available. If the design needs faster failover or read scale, add reader instances in different availability zones. The console makes creation easier. It does not remove the architecture decisions. Aurora is cluster-based. What creates the shared Aurora cluster configuration and storage layer? The Create DB cluster operation. What creates the writer or reader database compute inside that cluster? The Create DB instance operation. For a high availability design, do not stop after creating one writer. Consider whether the workload needs reader instances in other availability zones, then test the application's behavior during a failover. This is practical operations knowledge. The key cloud practitioner lesson is simpler. Aurora uses a cluster with writer and reader instances, not a single standalone database server. Choose Aurora MySQL or Aurora PostgreSQL based first on application compatibility and team skills. Aurora MySQL is a strong candidate for applications built around MySQL tooling, libraries, and SQL behavior. Aurora PostgreSQL is a strong candidate for applications already built for PostgreSQL features and its ecosystem. Both use the Aurora cluster architecture and can use reader instances, global database, and Aurora Serverless where supported. Neither engine choice guarantees an identical migration from a standard database. Test SQL behavior, extensions, stored procedures, drivers, performance, and operational tooling. Babelfish is an Aurora PostgreSQL feature that can help certain SQL Server applications connect and migrate with fewer changes. It is not a reason to choose Aurora PostgreSQL without a compatibility assessment. The real decision is what the application already expects and what its workload requires. Babelfish for Aurora. PostgreSQL can help some SQL Server applications migrate to Aurora PostgreSQL with fewer changes. It adds an endpoint that accepts SQL Server clients using the Tabular Data Stream, or TDS protocol. It also supports many commonly used SQL Server statements and tools, while the same cluster can still offer a PostgreSQL connection endpoint. But Babelfish is not SQL Server running unchanged on AWS. It has supported features, compatibility differences, and limitations. Before a migration, assess the application's TSQL, stored procedures, extensions, drivers, authentication design, and operational dependencies. Use Babelfish when compatibility testing shows it can reduce migration effort. Do not promise no rewrite, no testing, or no licensing decisions before that assessment is complete. One advanced name to keep separate: Amazon Aurora DSQL. Aurora DSQL is not an Aurora MySQL or Aurora PostgreSQL cluster. It is a separate serverless distributed relational database service for transactional workloads that need strong consistency and supported active-active multi-region operation. Aurora Global Database solves a different problem. One primary writer region, secondary regions for read scaling, and regional disaster recovery. Aurora DSQL multi-region clusters are limited to supported region sets, so it is not a universal cross-continent design option. For this beginner video, remember only the distinction. Global Database has one primary writer. Aurora DSQL is the separate distributed option for supported active-active designs. Let's make sure the advanced names don't blur together. Your company has a SQL Server application and wants to investigate whether it can move to Aurora PostgreSQL with fewer code changes. Which capability should the team investigate? Babelfish. But only after compatibility assessment and testing. Now another company needs a relational transactional application that can actively operate across supported multiple regions with strong consistency. Which service deserves evaluation? Aurora DSQL. And what if the requirement is different? The application needs one primary Aurora writer region, fast reads from secondary regions, and regional disaster recovery. That's Aurora Global Database. 3 different problems. Babelfish, SQL Server migration compatibility. Aurora DSQL, separate distributed relational architecture for supported active-active multi-region transactional workloads. Aurora Global Database, one primary writer region with secondary regions for global reads and disaster recovery. Know the distinction. You don't need to become an expert in all 3 for cloud practitioner. Aurora provides the building blocks for a secure database, but your team configures them. For encryption at rest, create the Aurora DB cluster with encryption enabled and select the appropriate AWS KMS key. For encryption in transit, configure database clients to use TLS with the engine's supported settings. Place the cluster in a VPC using a DB subnet group. For a typical production architecture, keep the cluster private and not publicly accessible. Attach a security group that permits the database port only from the application tier's security group. Some Aurora engine and version combinations support IAM database authentication, which can reduce dependence on long-lived database passwords. Verify support and operational requirements before adopting it. Encryption alone is not enough. Production security is layered: private networking, least privileged security groups, KMS encryption at rest, TLS in transit, controlled authentication, monitoring, and tested access procedures. Aurora often sits at the center of an application as the transactional system of record. Imagine an e-commerce platform. Customers place orders. Payments are recorded. Inventory changes. Customer information is updated. Those transactions belong in the operational database. But now the analytics team wants to analyze years of sales data. And the machine learning team wants to experiment with customer behavior. Should both teams simply run massive queries against the production Aurora writer? Usually that's not the architecture you want. The production writer has a critical job: process application transactions reliably. Eligible operational read traffic may use Aurora Reader instances, but large analytical or experimental workloads should generally use an appropriate analytics pipeline or integration pattern instead of competing with production transactions on the writer. Think of the architecture in layers. Application transactions flow into Aurora. Aurora remains the transactional system of record. Data needed for analytics moves through an approved integration or data pipeline. Analytics and machine learning systems work from the appropriate downstream platform. The exact AWS services depend on freshness requirements, security, governance, region, scale, and architecture. The important principle is simpler. Don't make your production transactional. Write or solve every data problem just because that's where the data starts. Protect the transactional workload. Design analytics separately. Aurora's MySQL and PostgreSQL compatibility can reduce migration effort, but compatibility is not a guarantee that every application works unchanged. Start with an assessment. Check the source engine version, SQL features, extensions, stored procedures, drivers, operational tools, performance expectations, and downtime tolerance. Then choose a migration method. Depending on the source and the required downtime, teams may use standard database backup and restore tools, replication-based migration, or AWS migration services. Move the schema and data. Validate query results and performance. Rehearse the cutover. Then switch the application only after the tests pass. For SQL Server applications, evaluate Babelfish separately. It can reduce change for supported workloads, but it requires the same discipline: compatibility assessment, testing, performance validation, and rollback planning. Migration is not dramatic when it is planned. It is risky when compatible is mistaken for identical. Aurora is a managed relational service compatible with MySQL and PostgreSQL. Its cluster architecture separates compute from distributed storage. Use reader instances for eligible read scale and as potential failover targets. Use Aurora Serverless when an ACU-based auto-scaling range fits the demand pattern. Use Global Database for multi-region reads and regional disaster recovery with one primary writer region. Then compare Aurora honestly with standard RDS. Choose Aurora only when its architecture, capabilities, and total cost fit the workload better. Do not choose Aurora for a benchmark number. Choose it for the right architecture. That's Aurora. Next in this AWS database series, Amazon DynamoDB, the managed NoSQL database built for massive scale. We'll cover when a non-relational database beats SQL and why DynamoDB shows up constantly on the Cloud Practitioner exam. If this clarified Aurora, subscribe and like so the next part lands in your feed. Don't finish this video by memorizing Aurora features. Design something that forces you to decide when those features actually matter. Here's your portfolio challenge. Design the Aurora architecture for an e-commerce application. The application already uses PostgreSQL. Traffic is moderate most of the year, but major sales events create large increases in red traffic. The company requires high availability across availability zones, and leadership is considering expansion into additional AWS regions. Start with the core cluster. Create or design an Aurora PostgreSQL cluster with a writer instance. Now add reader instances in other availability zones. Explain their two jobs. First, eligible read scaling. Second, failover targets. Show the cluster endpoint used for writer connections. Show the reader endpoint used for eligible read-only connections. Then show the shared Aurora cluster storage spanning 3 availability zones. Now add security. Place the Aurora cluster in the appropriate private database subnets. Keep it from being broadly publicly accessible. Allow database traffic only from the application's security group. Enable encryption at rest with AWS KMS. Use TLS for database connections. Now add recovery. Configure automated backups and document the recovery requirement. Next, address variable demand. Would provisioned Aurora capacity make sense? Or would Aurora Serverless better match the workload? Don't choose serverless simply because it sounds newer. Explain the demand pattern that makes it appropriate. Now imagine the company expands globally. Add Aurora Global Database to the design. Show one primary writer region and secondary regions used for local reads and regional disaster recovery. Then ask the most important question in the entire project. Why Aurora? Could standard RDS PostgreSQL meet the requirements at a lower cost and with a simpler architecture? If yes, say so. If not, document exactly which Aurora capabilities justify the decision. Your final architecture should show Application Tier, Application Security Group, Aurora Writer, Reader Instances across Availability Zones, Cluster Endpoint, Reader Endpoint, Shared Distributed Storage, Private Database Subnets, KMS Encryption, Automated Backups, and, as an optional extension, Aurora Global Database. Then create a README answering these questions. Why Aurora instead of standard RDS? How is Aurora's storage architecture different? Why do you have reader instances? What happens when the writer fails? What's the difference between the cluster endpoint and reader endpoint? When would Aurora Serverless make sense? When would Global Database make sense? And what security controls protect the database? Put the diagram and README in your portfolio or GitHub. Now imagine an interviewer asks, what's the difference between Amazon RDS and Aurora? Instead of saying, Aurora is faster, you can say, Aurora uses a different cloud-native cluster architecture. I designed an Aurora PostgreSQL environment with distributed storage, cross-AZ readers, read scaling, failover, private networking, encryption, and a multi-region extension. Let me show you why I chose it over standard RDS. That's an architecture conversation, and that's the skill you're trying to build. Careers aren't built by watching videos. They're built by applying what you learn. Go build it, document it, and be ready to explain your decisions. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.